Introduction. Why a storyboard approach? Throughout the previous activities, you have explored what DevSecOps means, how a continuous integration and continuous delivery pipeline works, where security checks fit in at each stage, and how artifacts and checkpoints protect a project from dangerous code reaching production. Now it is time to bring all of this together in a concrete, narrative scenario. A storyboard that follows a real-world style incident from its origins to its prevention, thanks to the practices you have studied. This storyboard is not fiction for entertainment. It is a pedagogical reconstruction of the kind of event that happens every day in software companies around the world. Reading it carefully will help you understand not just what DevSecOps does in theory, but how it operates in practice, step by step, on a real project. The setting: a growing e-commerce company. Imagine a company called ShopFast. ShopFast sells consumer electronics online. It has a development team of 12 developers, a small operations team, and no dedicated security engineer. Like many fast-growing companies, ShopFast has historically prioritized shipping features quickly over reviewing code for security issues. Their pipeline is automated but does not include any security scanning tools. ShopFast handles thousands of customer transactions per day. Their platform stores names, shipping addresses, email addresses, and payment card references. They are legally required to protect this data under data protection regulations. A breach would be catastrophic financially, legally, and reputationally. Act 1. The dangerous code is written. A junior developer named Lucas is working on a new promotional coupon feature. The feature allows customers to enter a coupon code at checkout to receive a discount. Lucas writes the back-end code quickly because the feature is due for release before a major sales campaign. He uses a database query that directly incorporates the user's input into the query string without sanitizing or validating it. In concrete terms, the query looks like this in logic. Select discount from coupons where code equals followed directly by whatever the user typed. This is a classic SQL injection vulnerability. If a malicious user types a specially crafted string instead of a real coupon code, they can manipulate the database query to extract sensitive data, bypass authentication, or even delete records. Lucas does not notice the flaw. He commits his code to the shared code repository and creates a pull request, asking a colleague to review it. Act 2. The old pipeline. What would have happened without DevSecOps? In the old pipeline at ShopFast, the sequence was simple: write code, run unit tests, merge into the main branch, deploy to production. The unit tests check whether the coupon discount is applied correctly to the cart total. They do not check whether the database query is vulnerable. The colleague reviewing Lucas's pull request is a senior developer focused on code readability and logic correctness. She confirms the discount logic works. She approves the pull request. The code is merged. The automated pipeline runs the unit tests. All pass. The code is packaged into a deployment artifact and pushed to the production server in less than 20 minutes. That same evening, an attacker who routinely scans e-commerce sites for vulnerabilities discovers the coupon field. He sends a crafted input string that causes the database to return the full contents of the user's table, including hashed passwords and email addresses. He extracts this data silently. ShopFast does not know for 3 weeks, when a list of their customers' emails appears for sale on a criminal marketplace. The damage: regulatory fines, customer notification costs, loss of customer trust, and a crisis communication effort that diverts the entire leadership team for months. Act 3. The new pipeline, DevSecOps in action. Now let's replay the same story with a DevSecOps pipeline in place. ShopFast has invested 2 months in restructuring their delivery chain. They have introduced several security tools and processes that activate automatically at different stages of the pipeline. When Lucas commits his code and opens his pull request, the following sequence unfolds. Static application security testing activates immediately. This tool reads the source code without executing it and analyzes it for known vulnerability patterns. Within 2 minutes, it flags Lucas's database query as a high-severity SQL injection risk. It points to the exact line of code and explains why it is dangerous. The pull request is automatically marked as failing a security gate. Lucas receives a notification in his development environment explaining the issue, along with a link to a remediation guide that shows how to use parameterized queries instead of string concatenation. Lucas rewrites the query using a parameterized approach. In this corrected version, the user's input is never directly inserted into the query string. Instead, the database engine treats it as pure data, not as executable instructions. The injection attack is structurally impossible. Lucas commits the fix. The static application security testing tool reruns and finds no further issues on this point. The security gate turns green. The pipeline proceeds to the next stage. A software composition analysis tool scans all third-party libraries used in the project. It detects that one dependency, an older version of a JSON processing library, has a known vulnerability that could allow an attacker to cause the application to crash by sending a malformed request. This is flagged automatically. The development team is notified. They update the library to a patched version before the artifact is built. The code is packaged into a deployment artifact. Before this artifact is promoted to a staging environment, a dynamic application security testing tool is configured to run automated attack simulations against the deployed application in an isolated environment. It attempts SQL injections, cross-site scripting attacks, and authentication bypass techniques. All of them fail because the code is now correctly hardened. The artifact passes all security gates. It is promoted to production. Act 4. What made the difference? Key lessons. The storyboard illustrates several critical principles that you have been building toward across this chapter and the previous activities. First, security must be embedded in the pipeline, not added at the end. In the old pipeline, security was implicitly assumed to be someone else's responsibility, or simply ignored. By the time the code reached production, it was too late to prevent the incident efficiently. In the DevSecOps pipeline, security controls are triggered automatically as part of the standard development workflow, without requiring a separate manual security review for every commit. Second, catching a vulnerability at the coding stage is dramatically cheaper than catching it in production. Research in software engineering consistently shows that fixing a bug in production can cost between 10 and 100 times more than fixing it during development. A regulatory fine, a breach notification campaign, or a reputational crisis multiplies this cost further. Third, the developer is not the enemy. The developer is the first line of defense. In the DevSecOps model, Lucas receives immediate, actionable feedback. He is not blamed. He is informed and equipped to fix the problem. The pipeline provides context, what the vulnerability is, why it is dangerous, and how to correct it. This creates a culture of shared responsibility rather than a culture of blame. Fourth, multiple overlapping security checks are more effective than a single check. Static application security testing caught the SQL injection in the source code before the application was even built. Software composition analysis caught a vulnerable library that static application security testing would not have detected because it was in an external dependency. Dynamic application security testing confirmed the hardened application resisted live attacks. No single tool covers every threat, which is why layering tools at different pipeline stages is essential. Fifth, artifacts are trustworthy only when they have passed security gates. An artifact is the packaged, deployable version of the application at a given point in time. As you studied in the previous activity on pipeline checkpoints and artifacts, an artifact should not be promoted to the next environment unless it has cleared the defined security thresholds. In the Shop Fast story, the artifact was only promoted to production after passing static application security testing, software composition analysis, and dynamic application security testing checks. Act 5. The broader impact. Security as a competitive advantage. Beyond avoiding incidents, the DevSecOps approach gives ShopFast something unexpected, a competitive advantage. Their release cycles are not significantly slower than before, because the security checks are automated and integrated, not manual and sequential. In fact, because issues are caught earlier, the team spends less time firefighting production incidents and more time building features. Customers and business partners increasingly require evidence of secure development practices. ShopFast is now able to produce audit trails showing exactly which security checks were applied to each release, which artifacts were approved, and which vulnerabilities were found and remediated. This level of traceability would be impossible with the old pipeline. Conclusion. From concept to practice. This storyboard is the bridge between the conceptual understanding you have built in earlier activities and the practical implementation work you will undertake in later chapters. You now understand how a real vulnerability, a SQL injection, enters a codebase, how it would have caused a serious incident in a traditional pipeline, and how a properly configured DevSecOps pipeline intercepts it before it can do harm. The key points to retain are: a vulnerability introduced at the coding stage can be automatically detected by static application security testing before the code is merged. Third-party library vulnerabilities are detected by software composition analysis during the build stage. Dynamic application security testing simulates real attacks against a running application in a controlled environment, confirming that the deployed artifact is resistant. Security gates at each pipeline checkpoint prevent vulnerable artifacts from being promoted to the next stage or to production. The cost of fixing a vulnerability increases exponentially the later it is discovered in the delivery chain. DevSecOps is not about slowing development down. It is about embedding security into the rhythm of development so that speed and safety are not in opposition. These principles will serve as the foundation for the quiz that follows this activity, and for every technical chapter you will encounter in the rest of this course.